Welcome back to the deep dive. So you've shared a really fascinating stack of sources with us, all covering the foundational science of physical chemistry.
That's right.
And our mission today is to cut through all the equations, all the jargon, and give you a comprehensive but conversational shortcut to really understanding how chemical reactions happen.
Yeah, not just what they are. If you want to control or, optimize a process,
Yeah.
doesn't matter if it's an industrial reactor or just an enzyme in your body, you can't just know the ingredients.
Right.
You need to understand the universal laws that dictate, well, three things. Is this reaction even possible? How fast can it happen?
Yeah.
And where does it all stop?
Well, we've distilled those three questions into what we're calling the three pillars of this deep dive: energy, speed, and balance.
hmm
Energy is the domain of thermodynamics. Speed is governed by kinetics. And that final state, that's defined by equilibrium.
And these three areas, they're distinct. They answer separate questions, but they are so fundamentally connected. We're going to look at each pillar and see what leverage points you actually have to control the process.
Okay, let's unpack this. Starting with the energy that drives the whole process, thermodynamics. And before we even get into the reactions themselves, our sources take us back to this theoretical limit for energy conversion, the Carnot engine.
Ah, the Carnot engine, developed way back in 1824. And it's not a machine you can actually, go out and build.
It's a thought experiment.
It's a thought experiment, exactly. But it's vital because it sets the absolute ceiling for efficiency. It estimates the theoretical maximum work any heat engine can possibly get from converting heat.
And for any engineer, that maximum efficiency is the ultimate and, well, frustrating goal they can never quite reach.
Right. Carnot developed this cycle as a completely ideal, reversible process. It has 4 stages, 2 where the temperature is constant, that's isothermal, and 2 where no heat gets in or out, that's adiabatic.
And the beauty of this model is it shows exactly why you can never get 100% efficiency. So why is that?
Well, the net efficiency calculation is 1 minus the ratio of the low temperature to the high temperature. So if you want 100% efficiency, that low temperature would have to be absolute 0, which is impossible.
Or the high temperature would have to be infinite.
Exactly. It just mathematically locks in the fact that you will always lose some energy to the cooler side.
Okay, so that establishes the theoretical limit, but what about the energy that's actually tied up inside a chemical reaction? And that brings us to enthalpy, or delta H.
Right. Enthalpy, delta H, is essentially a measure of the change in bond energy for a reaction, assuming you're doing it at constant pressure.
And the key for us is reading the sign. If delta H is positive, what's that telling us?
A positive delta H means the reaction is endothermic. It had to absorb energy from its surroundings. The products have more energy stored in their bonds than the reactant started with.
And negative.
If delta H is negative, the reaction is exothermic. It released energy, usually as heat.
But just knowing if a reaction gives off heat or absorbs it, that isn't enough to know if it'll actually happen on its own.
Not at all.
And that's where the true decision maker comes in. Gibbs free energy, or delta G.
Yes. Delta G is often called the available energy. It's the energy we can actually harness to do something useful. And this is where we have to bring in that other great thermodynamic force, entropy, or delta S.
The measure of disorder.
The measure of disorder or the dispersal of energy, yeah.
And that gets us to the crucial equation. Delta G equals delta H minus T delta S. You're balancing the bond energy against the change in disorder.
Exactly. And the sign of delta G is the definitive guide. If it's negative, the process is spontaneous. It'll happen. If it's positive, it's not spontaneous. And if delta G is 0,
you're at equilibrium.
You're at equilibrium.
Now, here's where it gets really interesting, because our sources highlighted a surprising fact. We sort of instinctively link spontaneity with exothermic reactions, right? Things that give off heat.
We do. We think if delta H is negative, it must go. But that's not always true.
Because of that entropy term.
Because of that T delta S term. You can have a reaction that is highly endothermic. I mean, it sucks in a ton of energy, so delta H is positive. But if that reaction results in a massive increase in disorder, say turning 1 solid molecule into 5 gas molecules.
So much more chaos.
So much more chaos that the T delta S term becomes huge and positive, and it can completely overwhelm the positive delta H. The universe just favors the disorder.
So the messiness is what makes it go.
That's right. So thermodynamics tells us yes or no. Is it possible? But, a spontaneous reaction could take 1,000,000 years to finish. We need a stopwatch. And that pivots us to our second pillar, kinetics. the need for speed.
Right, so kinetics, it's the study of the rate, how fast reactant and product concentrations change over time. Now, critically, thermodynamics only cares about the start and the end,
It's a state function, yeah.
but kinetics is all about the path you take to get there.
It's the difference between knowing your destination is downhill, that's thermodynamics, and knowing if the road is smooth asphalt or, a muddy track with 1,000 detours. That's kinetics.
So how do we actually measure the rate?
The rate is just the change in concentration over the change in time. And when we calculate it, we use the coefficients from the balanced equation to make sure the rate is consistent no matter which substance we're tracking.
And you can look at it in a couple ways. Average rate over a time period or...
Or the instantaneous rate,
Mhm.
the unique rate at one specific moment in time. That's just the slope of the concentration curve right at that point.
And researchers track these changes in real time using all kinds of instruments.
Oh, yeah. If something in your reaction absorbs light, you use spectrophotometry. If it's a gas reaction where the number of molecules changes, you can just monitor the pressure. Or even polarimetry for complex molecules, which measures how they rotate light. You just need a property you can watch continuously.
Okay, here's where it gets really interesting. Collision theory. Molecules are constantly just bumping into each other. So why don't all those collisions lead to a reaction?
Right. The energy needed to kick things off usually comes from those collisions. But for a collision to be an effective collision, one that actually works, it has to meet two main conditions.
Condition one is energy.
Correct. The collision has to provide enough energy to get over what we call the activation barrier. That's basically the energy you need to start breaking the old bonds.
And that peak on the energy diagram.
That peak corresponds to a very temporary, super unstable structure called the activated complex, or the transition state intermediate.
And condition two is orientation.
Even if they hit hard enough, they have to hit in exactly the right spot. I mean, imagine trying to build with Legos by just throwing them at each other.
The chances are very small.
Very small. For complex molecules, we quantify this with something called the orientation factor, P. If the geometry is really specific, P can be tiny, meaning only a fraction of 1% of collisions are actually oriented correctly.
So if we want to speed up a reaction, what are the practical knobs we can turn? Our sources list 6 key factors.
The first two are just about the materials themselves. First, the nature of reactants. Simple molecules react faster than big, bulky ones. Weaker bonds break more easily.
And second, the physical state. Gases react faster than liquids, which react faster than solids.
Which is why surface area is so important for solids. A big chunk only reacts on the outside, but grind it into a powder, you've just massively increased the surface area and the rate shoots up.
Then we get to the environment. Number 3 is concentration.
That's a simple one. More reactants packed into the same space means more collisions. More collisions means a faster rate.
And the fourth factor is, I think, the most powerful, temperature.
Oh, it's a huge lever. Increasing temperature means molecules collide harder, and crucially, a much bigger percentage of them have enough energy to clear that activation barrier.
And the rule of thumb is pretty amazing, isn't it?
It is. Most chemical reaction rates will roughly double for every 10 degrees Celsius rise in temperature.
Yeah. Double. For every 10 degrees. That's exponential.
It's huge. And it's why cooling is so critical in industry, to stop reactions from running away.
Okay, factor 5 is the one we turn to when we can't just crank up the heat. Catalysts.
Catalysts are amazing. They affect the rate, but they aren't consumed themselves. They work by providing a totally different reaction path, one with a much lower activation energy.
They don't change the start or end points?
Nope. They just build a tunnel under that mountain peak instead of making the molecules climb over it.
And finally, factor 6 is pressure, which is mostly for gases.
Right. Increasing pressure just forces the gas molecules closer together. It's the same effect as increasing concentration, more collisions, faster rate.
And you can break down catalysts into 2 types, right? Homogeneous and heterogeneous.
Yep. Homogeneous are in the same phase as the reactants. Heterogeneous are in a different phase. And in biology, I mean, you can't forget enzymes. They are the catalysts that make life possible.
So after we've manipulated these factors, we can figure out the reaction order by visualizing the data.
You just plot your concentration data in a few different ways until one of them gives you a straight line. If concentration versus time is linear, it's 0 order. If the natural log of concentration is linear, it's first order.
And the reciprocal of concentration gives you second order.
That's it. The visual test tells you the order immediately.
Fantastic. So we know if a reaction is possible with delta G. We know how fast we can make it go with kinetics. So now we move to the final piece. Where does the system stop? Equilibrium.
And equilibrium is a dynamic state. It looks like it stopped, but it hasn't. It's when the rate of reactants turning into products exactly equals the rate of products turning back into reactants.
So the net concentrations don't change. We define this final state, this ratio, with the equilibrium constant, keq.
Which is just a simple ratio, concentration of products over the concentration of reactants, all raised to their stoichiometric powers.
And the power of keq is that it's an absolute constant for a reaction at a given temperature. If you know K, you know what your final yield is going to be.
That's right. And interpreting it is so straightforward. A big K means you've mostly got products at the end. A small k means you're left with mostly reactants. And if k is near 1,
You've got a good mix of both.
a good mix of both. But you have to remember the rules. Pure solids and pure liquids never appear in the K expression. Their concentrations are constant.
Right. Now, K tells us where the finish line is, but how do we know where we are in the race? And that's where the reaction quotient, Q, comes in.
Q is your GPS. It uses the exact same formula as K, but you plug in the concentrations from any time, not just at the end. And then you compare Q to K.
So if my Q is less than my K, what does the reaction do?
If Q is smaller than K, your ratio of products to reactants is too low. The reaction needs to shift to the right to make more products until that ratio goes up and Q equals K.
And if Q is greater than K,
Then you've overshot it. You have too many products. The system will shift back to the left toward the reactants to bring that ratio down.
this drive to rebalance brings us to the final, really powerful idea here, Le Chatelier's principle.
It's such an intuitive principle. If you have a system at equilibrium and you disturb it, it will shift in a way that minimizes that disturbance. It fights back.
So let's take a disturbance. If I add more reactants,
The system wants to get rid of them. It shifts, right, consuming those reactants to make more products. If you pull a product out, the system rushes to the right to replace it.
what about pressure? If I shrink the container?
Increasing the pressure by shrinking the volume, the system will try to reduce that pressure. So it shifts to the side of the equation that has fewer moles of gas. It literally tries to take up less space.
And the trickiest one is always temperature, because now we have to go back to thermodynamics, back to delta H.
You do. You have to treat heat as if it's a reactant or a product. For an exothermic reaction, heat is a product. So if you add heat, you raise the temperature. It's like adding a product.
And the system shifts left to get rid of it?
Exactly. It shifts left, back to the reactants.
Yeah.
This means if you want to maximize the yield for an exothermic reaction, you should actually run it cold.
By pulling the heat out, you force it to the right to make more.
Precisely. And the exact opposite is true for an endothermic reaction, where heat is a reactant. Adding heat pushes it to the right.
Okay, but there is one critical caveat that links all this together, especially kinetics and equilibrium. What about catalysts?
Ah, yes. The catalyst. It speeds up the rate. It's all about kinetics. It lowers that activation energy. But it does not change cake.
So it doesn't change the final destination.
Not at all. A catalyst speeds up the forward reaction and the reverse reaction equally. It just helps you get to equilibrium faster. It changes the time it takes, not where the finish line is.
So what does this all mean for you? We've connected the energetic potential. Is it even possible? That's delta G. The speed constraints, how fast will it go? That's kinetics. And the final stable yield, what's the balance? That's equilibrium.
And this triad of knowledge is just, it's
Yeah.
fundamental. You have to use these levers. Can I make delta G negative? Can I lower the activation energy with a catalyst? How can I use the Chatelier's principle to shift K in my favor?
And for a final provocative thought, we saw that delta G predicts spontaneity and K describes the final outcome. Well, the sources show they are mathematically linked. K is proportional to the exponential of negative delta G.
Which is mind-blowing. It means that the fundamental energy potential of the reaction sets the ultimate unchangeable limit for what that product-to-reactant ratio can ever be. The universe dictates the balance.
You now have the framework to look at any reaction and determine its destiny. What process will you look at next using the knowledge of energy, speed, and balance? Thanks for diving deep with us.
So,